Okay, this is the last of the talks in this week's set. I'm going to talk a bit about the supercell approximation and then defects. So far we've always been working under this assumption that the systems we're describing are perfectly periodic, that they have crystal symmetries. I'm going to talk a bit more about what sort of simulations we can actually perform with plane waves, because plane waves are linked to this approximation of perfect lattice symmetry. So just to remind you, when we're discussing a periodic system, we kind of have a unit cell, and then we can imagine that this unit cell is just completely surrounded by repetitions of what's in the cell, and these just stretch to infinity. But we can actually construct supercells as well, so we don't necessarily need to use the smallest cell that would describe a particular arrangement of atoms, but we can make our cell bigger, and this is called a supercell. So the simplest thing you can do is just to double the size of your box in each direction, and this will produce what's called a 2 by 2 supercell. This is in 3D. We just keep on going with this approach and make the real space cell that describes our system bigger and bigger. So this will increase the numerical cost of the calculation, but as we make this real space cell bigger, it will also make the reciprocal space smaller. So this is one strategy of dealing with k-space sampling. Just make supercells. The amount of k-points you'd need to achieve the same accuracy will go down. So I did some of these calculations myself. There are some symmetry arguments that mean that k-points and supercells aren't exactly the same, unless you're considering odd cells. But I did some calculations on an MgO crystal, and I looked at how the area in energy as you both increase the number of k-points and increase the size of the supercell representation. You can see that these are the same thing, so for these odd numbered calculations. So to get a really well described wave function for a crystal, we either need to use a big supercell or we need to use k-point sampling and use more k-points. In both cases, though, you can see the convergence is not smooth with respect to k-points or with respect to supercells, which is a shame. But it means that for this type of convergence, increasing the number of k-points we use or the size of the supercell might not actually make our answer better, but it will, as we systematically add more and more, it should improve the quality of our answer. So it makes convergence a bit trickier to judge than something like cutoff energy, where you do generally just see straight improvement. So although we've developed an approach that's based on this kind of ideal symmetry, it doesn't mean that we can't use it to simulate things with less symmetry, but that symmetry will then play the role of being an approximation we force on the system. And the symmetry that's forced on the system will depend on the size of the simulation cell we used. So it'll become an important parameter again to understand in terms of the accuracy we want to achieve. So one example of a non-crystalline system we could study would be something like an amorphous material. So amorphous materials are disordered, they don't have crystal symmetry in their structures. But what we could do is we could use something like plane wave DFT to simulate a block of amorphous material. So this block can be completely disordered within the block, but then when we put this structure into plane wave DFT, it will then just surround this block with infinite repetitions of this disordered block. So you can kind of see it if you imagine it, but basically as we make these disordered blocks larger and larger, then it will be a better and a better description of a completely disordered system. But then the size of the model we constructed becomes an important parameter that defines how reliable our calculation is, because it describes the amount of symmetry that we enforce on this non-symmetric system. Another example that we could look at in terms of this supercell approximation is to look at defects. So, I mean, there are a few different sorts of crystalline defect you can get. Just summarized some of the most commonly seen crystal point defects, I should say, on this slide. So we've got quite a few possibilities for how crystal structures can be damaged in the real world. So if a crystal has no defects, that would mean it has ideally low entropy. but according to thermodynamics, we're never going to have a state of ideal entropy. So there's always going to be some defects in a crystal that act to increase the entropy of the arrangement, no matter what we do. You can get things like vacancies, which is where an atom is missing from its crystal site. You can see that the atoms around it will distort due to the presence of this missing atom. We can get interstitials, where atoms are not sitting on lattice sites at all, but they're kind of sitting at some point in between, kind of an additional atom. We can get substitutional defects, where a different chemical element has placed an atom in the lattice where it shouldn't be. And we can get things like Frenkel pairs, for instance, which is a pair of a vacancy and interstitial that's very commonly seen and formed, where one of these atoms has kind of wandered off its lattice point and ended up in an interstitial site somewhere else in the lattice. So in practice, there's quite a lot of ways the perfect symmetry of the lattice can be disrupted by point defects. And we could simulate this using the supercell approach. So we can put a vacancy defect, say, in our unit cell. And then what we would have, if we imagine the infinite repetition of this cell, is just an infinitely repeated pattern of this defect structure. So if we remove an atom from quite a small cell, then this crystal will be very substoichiometric. It will have a lot of missing atoms. So it'll behave quite differently, most likely, than the bulk material would. But as we increase the size of the supercell, which we introduce this vacancy defect in, it actually decreases the concentration of these defects considerably. So we use larger and larger cells, then we get less and less of these defects. So we can make the argument, and this is often done, that as we increase the size of these supercells, we get closer and closer to recovering the properties of just an isolated defect. We just have one defect in the crystal lattice. This is something that's done commonly. But what we'll find is that the size of the supercell we've used then directly affects all the properties we calculate for this defect. And as we make the cells bigger, then the errors introduced by the repetitions will decrease. So you can normally define the total energy of the formation energy, I should say, of a defect, how much energy it costs to form, in terms of doing a DFT calculation with a defect in a supercell and subtracting off the energy of a DFT calculation of a supercell of the same size but without the defect in it. And then you can also add in a chemical potential term. Because when we remove an atom from the DFT calculation, it's like it just vanishes, whereas in reality, the atom has gone somewhere. So we can associate a chemical energy, a chemical potential with where the reservoir the atom's been exchanged with to make our definition more realistic. But how much this supercell approximation affects the accuracy of things we calculate will really depend on the examples we consider. So for instance, if we were to consider what's called a neutral F center in magnesium oxide, we'd find that the errors that the supercell approximation introduces are quite small. So an F center is a particular type of defects in magnesium oxide where an oxygen atom is missing. It's an oxygen vacancy defect. I'm going to murder the pronunciation, but this phrase, this name F center comes from the German word Farbe, which means color, because these F centers, when they're introduced into a crystal of MgA, they change the color of the crystal, because the crystal has, the defect has a localized electrons bound in the vacancy, and these can interact with photons and change the color of the entire crystal. But what I've plotted here is a plot of inverse defect separation. So the inverse of how far these defects are apart from each other. So this is a 1 by 1 by 1 cell. This is a 2 by 2 by 2. This is a 3 by 3 by 3. This is a 4 by 4 by 4 cell. And what you can see is that the formation energy of this neutral defect doesn't really depend on the size of the supercell much. So for some systems, the use of this supercell approximation won't introduce much error into the total energy of the system, and we don't need to use really big supercells in order to get accurate results. For this particular example of defects, one example of systems where that's not true is where we start to charge up this defect, this vacancy defect. So I've got some results here for a vacancy defect in a carbon in diamond structure. But what we've done is we've also removed 2 electrons from this defect. So it's got a net charge of +2. And then what you see is that you see much stronger size dependence in the size of the supercell that we use and the tail formation energy we calculate. In particular, it's often described in terms of this empirical relationship where you have length and volume dependent errors with your model. So this here is a cell with not 8 atoms. And we then remove 1 to form the vacancy defect and then calculate the formation energy. And you can see that as we go up to larger cells, all about to a supercell containing 512 atoms, where we then remove 1 of them to form the vacancy. We see even that is not a fully converged energy. Often for these sorts of problems, then there are methods that have been developed in order to make these calculations more accurate without requiring us to use really big supercells. And that's definitely the case for charge defects. So in the case of charge defects, it's found you need to add in a couple of corrections. You need to add in a term that removes all the electrostatic interactions between this charge defect and the neighboring unit cells, and also between a Jellian background. So plane wave DFT by its nature only really looks at neutral systems. So whenever we introduce a net charge like this +2 center, we always have to put Jellium into the system and structure this electric charge spread out across the whole cell that compensates the charge. This is part of the reason why these results are so dependent on the size. This is a general point. When you're simulating charge systems under periodic boundary conditions, you're always going to find the results are very dependent on the size of the supercell you use due to this Jellium compensation. And there's additional problems as well related to the alignment of the potential, which is always a little bit tricky in plane wave DFT. Another example of this that's commonly seen is work function calculations for surfaces. Again, in that situation and in this situation, you need to be a little bit careful about what you're referencing your potentials to. Yeah, and this is another property of plane wave DFT, is that we actually can't calculate the average value of the potential inside our system. So conventionally it's set to 0, or you can set it to whatever you want. And this means that when we compare different plane wave DFT calculations, their potentials might be shifted by an unknown constant. This is what happens with the bulk systems and the defective systems. This is again generally true for plane wave DFT. Like if we were doing surface calculations of a different size, for instance, we wouldn't be, the average potential might not be the same in the 2 systems. And the way you typically see that is the vacuum potential is different. The potential that represents empty space outside your surface. So in this particular example of charge defects, this alignment effect is a smaller source of the error. So this red line is uncorrected and this blue line is with potential alignment. Indeed, in this case, adding the potential alignment makes the results worse at this stage. But then if we include an electrostatic correction as well, then we're able to remove a lot of the size dependence. So a combination of corrections can remove a lot of the supercell size dependence from these calculations. But anyway, there's a few particular points that I really wanted to emphasize from what we've covered today. And I guess the main thing is that we can use plane waves and pseudo potentials very successfully to simulate materials. But it's important, and we'll perhaps discuss this in more detail next week, it's really important when we're doing these sorts of calculations to understand the convergence of the numerical quality of our calculation and what accuracy we've actually achieved. So, we've got kind of more direct approximations like the pseudo potentials we used, but we've also got more numerical features like, did we use a high enough plane wave cutoff to reproduce the system we're interested in? Did we use enough K points to sample the Brion zone? Was our supercell large enough that we didn't need to use K points? I mean, particularly on this point of pseudo potentials, they can allow an enormous reduction in the cost of your calculation, especially as you put more and more of the electrons into the pseudo potential rather than explicitly treating them in a DFT calculation. But it always means we need to be a bit careful with our calculations and check as much as we can against what's known experimentally and what's known through other calculations, because if our pseudo potentials are bad, it doesn't matter what we do with the rest of our convergence parameters, we just might not get good results. solution there is to change this to pseudo potentials that work better for our situation. But when when there are problems with pseudo potentials, they might not be particularly obvious. So we need to be careful always. And also just this final point, a bit more applied to examples, which I'll use defects as the example. We can actually use these plane wave approaches to study non-periodic systems like defects and surfaces. But in this case, we get this additional idea of this convergence parameter of the supercell size, where we need to try and use a large enough supercell that we don't introduce additional errors through the use of the supercell approximation.